Looking at objects in motion relative to reference frames is essential in physics. The basic idea is that the objects in motion are viewed relative to points of view, which are called reference frames. Take an example. Imagine a ball rolling away from me at a velocity x. Right now, we are observing the ball in my stationary reference frame. However, all physics plays out the exact same way if the viewer were to take the ball's perspective. In this example, I am moving away from the ball at the same velocity but in the opposite direction, namely negative x. Simple enough, right? Well, special relativity makes things a little more confusing. Thanks, Einstein. Special relativity, as the name suggests, is physics in special circumstances, namely at high velocities and in inertial reference frames, which are non-accelerating. Let's take an example. Imagine this. Instead of this being a ball, it's a photon moving at the speed of light. Also imagine that I'm moving at an extremely high constant velocity as I launch the ball up. Now the relative distance that this ball traveled in my reference frame is less than the relative distance that a stationary observer would have measured. This is because the ball traveled straight up and straight down relative to me. However, an observer would see that the ball is moving laterally as well. If the distance is less in my reference frame and the time is the same, that must mean that the relative velocity is less as well. And this makes sense because I was moving with the ball. However, many studies by many scientists have shown that the relative velocity of light is constant, even if the reference frame is moving. This means that either time or distance change. This is called time dilation and length contraction. Because we know for sure that the relative velocity in both reference frames was the exact same, and the distance measured in my reference frame was actually less, that must mean that time slowed down in my reference frame. In fact, calculations show that time slowed down in my reference frame relative to the stationary observers by a factor of 1 over the square root of 1 minus my velocity squared over the speed of light squared. This factor is always greater than 1 because my speed will always be less than the speed of light. That means that 1 unit of time in my reference frame is equal to 1 unit of time in the observer's reference frame multiplied by that factor. We can take this even further with length contraction. According to length contraction, the width of the photon in my perspective is actually larger than the width of the photon in the reference frame of the observer. Let's go back for another thought experiment to see why. Say the observer wants to measure the width of this ball, which is going close to, but not at the velocity of light. All they have to do to make things easier is measure the amount of time it takes for this ball to pass through the ring from start to finish. The reason for this is that we know the velocity is constant, but once we know the amount of time it took for the ball to pass through, we know the distance. In this case, the distance represents the width. However, when I measure that time, the time is longer by the factor that I mentioned earlier. And because the time is longer, that must mean that the width I measure is longer as well. It really is crazy, isn't it? That's special relativity in a nutshell.